In this example, sometimes it's helpful when we're solving problems with two objects to treat those two objects or more objects as if they're one. Now we can do this when all of the objects in our problem have the same acceleration. So in this example, we have two blocks. One has a mass of 3 kilograms, one has a mass of 5 kilograms. They're sitting together on a frictionless plane. You're going to notice a lot of frictionless planes before we talk about friction. So very soon, we will have a friction relationship and we'll use it in problems, but for now we're going to ignore friction. Someone pushes on the 3 kilogram block with a force of 7 newtons. Determine the acceleration of the blocks and the force exerted on the 5 kilogram block by the 3 kilogram block. So the first thing I'll do to solve this problem is I'm going to solve it by drawing two separate free body diagrams. And then afterwards, I'm going to show you how you would solve the problem if you lumped both of those objects together and assumed they were a single object. We can do it in this problem because both objects have the same acceleration. So first what I'm going to do is I'm just going to break this into two. I'm going to solve this the same way we've solved all our problems so far. I've got two objects, so I'm going to draw two free body diagrams. Here's mass A. So the forces acting on mass A are the force of gravity. I'll call that FGA, which is down. The normal force, so the force of the surface pushing up on block A, which I'll call FNA for block A. There's an applied force to the right. So I'll call that applied, force applied. And there's also a force that's pushing back on block A due to the presence of block B. So I'm going to call that FBA, which is our interaction force in this case. These are two objects that are touching, so there's an interaction force between them. That's all the forces for block A. Now for block B. This is the larger block. The force of gravity is different than block A, so I'll call that FGB. The normal force I'll call FNB. And there's actually only one force that's acting on block B, and that's the interaction force between blocks A and B. So I'm going to call that FBA. Notice that FBA is the same magnitude in this diagram as in this diagram, and that's because it's an interaction force. So the force due to block B pushing back on block A is equal in magnitude but opposite in direction to the force of block A pushing on block B. So that's an important thing to consider when we analyze these. I'm going to need a coordinate system. I'll call this my y direction, which is really boring in this case, and that's my x direction. So those will be my positive directions. It doesn't really matter which ones you choose. If we look in the y direction for a second, it's actually quite boring. In the y direction, I've always got a normal force and a force of gravity. Since there's no acceleration vertically for either block, I know that the force of gravity and the normal force acting on each block have to be the same in magnitude. So the net force in the y direction is 0 in both of these free body diagrams. So I'm actually not going to write an equation down for the y direction here. I am interested in the x direction. So I'm going to write for this diagram first for block A, F net in the x direction equals ma. And I know there's a non-zero acceleration for both of these blocks. So in the x direction, in the positive x direction, I've got my applied force. I've got the interaction force in the negative direction, and that's equal to ma. Keep in mind, the acceleration of block A is equal to the acceleration of block B, which I'm just going to call A from this point out. So that's what I have in this direction so far. And one thing I should do is distinguish between the mass of block A and the mass of block B, because that's going to be important really soon. In this direction, I'm going to write the same thing. F net in the x direction is equal to the mass of block B times its acceleration, which again is the same as the acceleration of block A. In this direction, it's a little bit easier. The only force in the x direction is the interaction force between the blocks. So now I've got these two equations written down, which is pretty good. But now I can make a little bit of simplification here. I have the interaction force between block A and block B over here and over here. So what I can do is substitute one into the other. So I'm going to take this equation right here, and I'm going to sub it into this equation so that I'll only have one unknown. I know the applied force that was given. Now I'm substituting in this equation over here. So the interaction force FBA is equal to MB times A. I'm going to drop the vector signs at this point. And that's equal to the mass of block A times A. So now I'm just going to do a little bit of rearranging. I'm going to move both acceleration terms to the right. Now on the right-hand side, I have two terms. Both of them have this acceleration in them. So I'm going to factor that out. So now I've really just got the sum of the masses in brackets here. To rearrange this equation, I'll divide both sides by MB plus MA. Same thing over here. And now I can figure out what the acceleration is. So in my next step, I'll just substitute in the numbers that I'm given. The applied force was just 7 newtons. Mass B was 5 kilograms. Mass A was 3 kilograms. So that gives me 7 divided by 8, keeping track of significant figures, which gives me 0.875 meters per second squared to 2 significant figures, and that's in the positive direction. So that's one way to solve the problem. I drew 2 free body diagrams for the 2 masses that I was given. I wrote out Newton's second law for both of them, F net equals ma. I did a little bit of substituting and I solved, which isn't too bad. However, I did have to draw 2 free body diagrams. So here's another way of doing it. Will give you exactly the same answer. I'm going to treat both of these objects as if they're one, and I can do that in this case because they have the same acceleration. So here's my amalgamated object, and I'm going to call that mass AB, so it's all of them put together. So in this free body diagram, the force of gravity is acting on that big lump. I'll call that AB. There's a normal force, which is acting on both masses. I'll call that normal force, AB. And there's an applied force, the same applied force as last time. There's no interaction force, because now, if I'm lumping both of them together, the interaction force is internal. So that's not going to affect its acceleration. I'm going to use the same coordinate system as last time, so right is positive. Again, nothing exciting is happening in the y direction. So I'm not going to write out F net equals ma for the y direction, but I will write it out for the x direction. So F net in the x direction is equal to the mass, which now is the mass of both objects together, times the acceleration. In the x direction, the only force is the applied force, and both masses together, that's just ma plus mb. This should look familiar, because it's the same equation from last time, except we came to it much faster. So that's exactly the same equation we came up with last time, except we had to draw 2 free body diagrams to do it. So in the end, I get exactly the same answer, 0.875 meters per second squared, 2 significant figures, except my solution is much smaller, much shorter. Therefore, the acceleration of the blocks is 0.88 meters per second squared. I guess I shouldn't say forward. I'll say right.